Evening all. You're next.
Okay, this is a summary of what you're about to see. I'm basically repeating Ian's experiment, but using clay, because clay doesn't really have any spring-like properties as such. Next, so the one mass weighs 496, dropped from 1060 millimeters, and the two mass weighs 996. In other words, that's 4 grams over actually. Dropped from 265 millimeters. The obelisk-shaped pug starts at 110 millimeters long each time, pressing it back into shape the way Ian did. 2 runs of 2 mass at V1. All 4 sides measured to average any small discrepancies, in most cases anyway. The first one came out at 102 millimeters long, so that's 8 millimeters displacement. I kept looking at it and thinking, is it 102 or 103? So you might argue that's more like 7.5 millimeters displacement. Anyway, and the second run where I did measure all 4 sides, that came out at 101, 9 millimeters displacement. So the average I'm calling 8.5 millimeters displacement. It might be fair to call it 8 millimeters really, but anyway, whatever. And the 2 runs of the one mass V2 that came out at 95 millimeters long, in other words 15 millimeters displacement, and then the second run 94 millimeters, 16 millimeters displacement, so obviously an average of 15.5 millimeters displacement. So the ratio I calculate to be 1.82 to 1. Could have been a little bit more if this run A actually was more like 103 long, but anyway, whatever. It's close enough to prove the point that the result shouldn't be 1.4 if we're trying to get an accurate reflection of the energy just by halving the mass but dropping it at the same velocity. I meant to say double the velocity then. There's no earthly reason why that should come out at 1.4 in my opinion. Even though I do like math skills, that's my opinion. I've stuck my head above the parapet, I disagreed with everybody, and been called a math denier, for want of a better expression, effectively. Such is life. When we apply half mv squared, let's say that the masses were 5 units and 10 units, and the velocity was 2 units and 4 units, just to keep the numbers simple to work with. In case 1, the lowest drop of the 2 mass, then if we halve the mass of 10, that's 5, then the velocity of 2 squared is 4, 5 times 4 is 20, and that represents the energy. But in case 2, the highest drop of the 1 mass, then if we halve the mass of 5, that's 2.5, then if we square the velocity of 4, that's 16, 2.5 times 16 is 40. So we've doubled the energy. Obviously, the energy is doubled and the ratio should be 2 to 1, not 1.4 to 1. I don't really know what John was on about, trying to imply it should be. Oh, anyway, I'm not going to go there.
Evening all. It's the filth.
I'm not going to fuck about. Are we back to Flintstone version? So we've got a pole dangling off this device here. Super sharp blade. Sharpening, anyway. That's not important right now. 1060 height to the bottom of that mark. 265 to that mark. Made a plunger device similar to Ian's where that inserts inside the tube. You know the story because he's already showed you. That goes inside the tube, same as Ian's, and the pug rests on that copper plate there. 2 of these weights. I think this was 485 and that was 495 grams. So I added 3 pennies to it to make it 496. That'd be 497 now with the glue added. That'll be double the mass. I'll just tape them together, whatever I want to do it. I've not even tried this yet. I'll tape these together first to make the 2 mass. 994. What's 994 divided by 2? It's 497 then, isn't it? Yeah. So each one should be 497 now, really, about right. That's Bob on 111. Forgive me, folks, but I keep calling this measurement 111 instead of 110 millimeters. It's because I'm so tired for whatever reason, and I still am. Insert the device, and this device will rest on there. I need to raise it to the height of that mark there. Cunning from twat. bloody see a thing. Oh, that's it. Right, so measure that now. 102. 102. Yeah, 102 I think. Possibly 103 actually, 103. Measure from the other side. It's gone a bit skew with oh, but it comes out the same. 102. Right, I've hammered it back to the 11 again. So 110. Oh, it's a load of piss balling about, isn't it? Let me put that back there. See that there. Rest it on there. Get this back to it. 3, 2, 1. Right, here we go. 102. Check the other side. 101. 100. 101. Yeah, I'm going to call this 101. I'm going to call this 101 because it measures a little bit different depending on which side you're measuring. In other words, it's not remained absolutely square. Looks it, but anyway, 101. Hammer it back into shape again. Okay, I've got it back to 111 now. I keep calling this measurement 111 instead of 110 millimeters. 110 rather, 11 centimeters. Camera is shit. The one that's at twice height now, so take the sellotape off this. Then I put the half mass on there. Put the plunger in here. Take this to 4 times higher. Sorry, you can't see the whole thing, but I suppose you need to, so let me just lift the camera for a moment. You can see. There's no way I'm going to fit this all on the thing, so I'm just going to have to trust me. Let's have a look what that did. Let's measure that now. Oh. It stayed square anyway, but measure that. We had 102 last time, didn't we? And now we've got 94. 94. Measure from the other side. 93. No, 94 again. 94, 94. 97. 96. What's the average of that? I suppose 95 was the average, isn't it? So, I suppose if you want to see those results, I read that as 94. It's a little bit sloped, so I'm measuring in the middle of that slope there. 93, 94 again. Anyway, I've averaged it out at 95. I think this side a bit more like 96. Yeah, 96. I'll do one more of that run and then call it quits to show you how I'm just reshaping it pretty similar to how just slap it on all 4 sides and to lengthen it and get the ends square again, you know. Let me see what this dimension is at the moment. Am I over or under 110 centimeters? Still well under. Hammer it a bit harder. Try harder, Steve. Come on, put your back into it. My fucking bad back. Every time I do this, I end up miles over, so square the ends up. I was going to make a mould, but by the time you prise something out of a mould, it's distorted anyway, so I'll probably still end up having to do this. It works out anyway. That looks nice and square, but is it the right dimension? That's it, bob on. Yeah. Put that there again. Put the half mass on the bar and the insert plunger tool thingy. 4 times height. I wonder how that works out. Looks quite square. So measure it. 91. Get to the side. Next side. 93. 91, 93, 95, and 93. So an average of 93 then, I think. Average of 93 because it's kind of sloping up a little bit. So that end measures 95, that end measures 91, and the middle 93. Well, it depends which side you're measuring from, you know what I mean? I'm trying to just average it out fairly. 93, I think that's fair. That's 90. I'd say 94 there actually. 92. 90, 94, 95. That looks more like 96 now. So I'm going to call it 94. Err on the side of caution. 94. 94. Call it quits now. Okay, sorry this is going to end up a little bit longer than I expected to explain, but I need to clarify a few things. Right. By rights, to get a good indication of the relative energies in the two cases, I'm sure that we should be measuring the volume displaced, not just the reduction in length of the pug, which is getting fatter the more it's compressed, and therefore harder to compress the more energy we are trying to measure. Surely that makes sense, yeah? So the higher the energy of the half mass dropped at twice the velocity is surely being under-registered, isn't it? Yeah. So perhaps we should also be measuring the increase in girth to calculate the actual volume displaced. Well, I've wasted 2 or 3 hours of my life trying to accomplish this, but ran into the following difficulties. It's practically impossible to uniformly shape the clay so that we can take reliable measurements. Every correction we make squeezing the block between two parallel surfaces, say, causes the other surfaces to distort so that they too need correcting again. So it's kind of an endless process, really. I'm only talking about very small differences, but very small differences make a big difference to the volume calculations because all the dimensions are obviously multiplied by one another. Arguably, we could use harder clay to minimize this problem, but that would exaggerate the next problem, the measurements. So problem number 2. It's hard to actually take accurate measurements by eye using a ruler, which is all I've got. Ian used calipers, which I don't have, but even then I think we really need to be measuring down to tenths of a millimetre for the volume calculations to be reliable. So perhaps some kind of laser measuring device might be called for in an ideal world. It's certainly not got one of them. And as hard as I've tried to take accurate measurements of accurately shaped blocks in the 3 different states of compression, the initial starting height, then the first compression stage, and then the second compression stage, which I've labelled there A, B, and C. The volume calculations just do not tally sufficiently well to make it worth all that effort. This is the same lump of clay that has been reshaped, so the volume in all 3 cases must really be the same. But errors in critical measurements lead to over 7% error between A and C, and nearly 3% error between B and C. Now, this error is comparable to the 5.96% error if we were to assume that the 1.414 was the correct result, the correct outcome for the one mass at 2 times velocity in Ian's recent test using cylindrical playdough, using its most reliable early results before cleaving became an issue. I think that was the main point of his experiment, to show that it was unreliable, giving virtually identical results after the first 7 or 8 runs, regardless of the masses and velocities. Problem number 3. Even if we can initially shape the clay uniformly enough to take accurate measurements once it's been compressed by the experiment, it doesn't expand outwardly evenly along its length. So the best we can then do to take measurements is to reshape it to that length, minus whatever distortions it incurred. It tends to bulge out in some places more than others, so the surfaces are no longer truly flat in the case of square profile blocks. And this might be less obvious for cylindrical clay. Even having reshaped it, I've taken measurements in 3 places along its length, hoping to make acceptable approximations, but I've got errors that I've mentioned a moment ago. All I can say with any certainty is that the girth figures do increase as it's compressed, and that's obvious, of course, and I can measure them, but just not accurately enough to make it worth the effort of trying to find the volume displaced. In Ian's second attempt using square profile blocks, he achieved a 1.5:1 ratio, exceeding his previous attempt with cylindrical Play-Doh, which came at 1.33:1, if I remember correctly, using his most consistent early results before cleaving. Those are the results that Michael applied. That was deemed to be a decent representation of the 1.414 square root of 2 result that everybody appeared to be convinced was the correct result for a half mass dropped at twice velocity, whereas I contended that it should have been 2:1 ratio for the following reason. And this is important, surely this is important. When we apply half mv squared, let's say that the masses were 5 units and 10 units, and the velocity was 2 units and 4 units, just to keep the numbers simple to work with. In case 1, the lowest drop of the 2 mass, then if we halve the mass of 10, that's 5, then the velocity of 2 squared is 4, 5 times 4 is 20, and that represents the energy. But in case 2, the highest drop of the 1 mass, then if we halve the mass of 5, that's 2.5. Then if we square the velocity of 4, that's 16. 2.5 times 16 is 40. So we've doubled the energy. Obviously, the energy is doubled and the ratio should be 2:1, not 1.4:1. I don't really know what John was on about, trying to imply it should be. Oh, anyway, I'm not going to go there. My repeat of Ian's experiment using clay yielded 1.82, and I'm quite certain the only reason it didn't come out at 2:1 is because of the inherent inaccuracies that I've already explained here. Taking the measurements of clay which isn't really as accurately made as we want it to be. When I say clay, I mean Play-Doh or any other material, really. I think that's the beauty, really, of the original experiment as done by Willem Gravesend, what his name is, or Emily de Châtelet, and anybody else who did it. Just dropping lead balls into clay. I think the earliest version of the experiment was the best one so far. Fuck all that Mythbusters nonsense. Anyway, that's my opinion. For what it's worth, thank you for listening. If you have done, good night and God bless.
Hello. What have we got here then? Somebody abusing the laws of physics. This is the clay police. You better watch your fucking step.